Thank you, Elspeth. Morning, everyone. So today I'm going to talk to you about a group of mammals called tenrecs. Tenrecs are native to continental Africa. So a few species that you find only on the mainland, but most of them, so the majority of tenrec species, are native to Madagascar. And the thing about tenrecs, or one of the interesting things about tenrecs, is that they look really, really different from one another. So, I mean, you have tenrecs, so you have burrowing species, you have kind of shrew-like species. You also have these species that have convergently, with hedgehogs, evolved like prickles. And so where did tenrecs go sort of fit in the phylogeny? So before the advent of molecular phylogenetics, back in the days of when morphology was the only way that we knew how to group animals together in the tree of life, tenrecs were put in this big group called the insectivora, which included, tenrecs at the bottom here, hedgehogs, moles, golden moles, shrews, and these things called selenodon, which are from Caribbean. But when DNA and proteins came in sort of in the 90s and early 2000s, that caused a rather major shake-up of the mammalian tree of life, and particularly of this old insectivore group. Tenrecs and golden moles, it turned out, were actually more closely related to elephants than they were to any of these other taxa that they'd been previously grouped with. And so after that happened, what had previously been thought, oh, these taxa were related, they then became this kind of pin-up case of convergent evolution. It's like, wow, these things look so close that we actually thought that they were related to each other, but they're not. But in a lot of cases, no one's had actually, I mean, I was interested in this problem because no one's really tested just quite how convergent they are. I mean, they look kind of similar, but how deep does it run? How are they really doing the same things ecologically? How similar are the evolutionary pressures that have shaped their evolution? And so that was kind of what I wanted to answer with this project that I've got myself involved in. And so how we went about answering this question, some colleagues of mine went around a ton of museums and photographed a load of skulls and lower jaws of various tenrec and other insectivorous mammal species. I'm only going to be talking about the jaws today, but we do also have a ton of skull data. And so from the photographs, we got landmarks. So we've got the red fixed landmarks, and we've also got these blue semi-landmark curves. And between that pretty much captures all of the whole outline of the jaw. From that, I did my sort of standard geometric morphometrics protocol. I did my general precrucites superimposition to get rid of any effects of rotation or translation. And then from there, I sort of took it in several directions. You did sort of standard principal components analysis and generated some morph spaces. But I also wanted to try some other clustering methods to see how things clustered based on their morphology and how that compared to what we know the phylogeny looks like. But also on top of that, once I got my principal components, I used the scores from them as a kind of smaller trait data set. And once I got this new trait data, I could use that to look at some other ways of testing and measuring convergent evolution, of which there are many. So just quickly outline a few of them. So probably the easiest way of thinking about convergence is just phylogenetic versus phenotypic distance. How far apart are they on the tree versus how far apart they are morphologically. You can also do the surface modeling, which looks for convergence in evolutionary regime, an adaptive regime. So you fit a series of evolutionary models on your tree, and if things are convergent, then they will be modeled. Basically, you fit the same model to different branches because they're evolving towards the same morphological optimum. I mean, there are also other measures like the C metrics that Tristan Staton came up with, which measure the amount the amount of morphological distance that evolution has closed between two taxa. I'm not really going to be talking about these as much. I'm mostly going to be focusing on results from this and this. And speaking of my results, here are the first batch. So these are just some principal component morph spaces that I generated. I've got my taxa color-coded, so Tenrex are this purple, sort of pinkish purple group here. And so you can kind of see that they do overlap with some other groups. So this, so the blue one is European moles, and well, like, so just normal moles, what you'd think of as a mole. And the yellow one is hedgehogs and friends. Probably the biggest take home from this graph though is that up here, golden moles, which have a sister group to Tenrex, they're just off, they're doing their own thing. Golden moles are weird. That's actually been the main thing that I've taken away from this project more than anything about convergence, is that golden moles are weird. But so just by sort of eyeballing these plots, you can see that Tenrex do seem to have a morphological affinities to things that they are not related to phylogenetically. This is a sort of an alternative way of visualizing that is this. This is a clustering dendrogram. This is just based on morphology. This is not a phylogenetic tree. This is not a phylogenetic tree, which is important because, so again, the color coding along at the bottom, same as before. This cluster is just composed of golden moles, because as I said, they're just off doing their own thing. But in this cluster here, which has all the Tenrex in it, they're sort of interspersed between, again, some of the moles and some of those hedgehogs. And so they're sort of all mixed in. But then there is also this other cluster over here, which contains the rest of hedgehogs, the rest of moles, shrews, and selenodons. If you kind of, you can sort of also visualize these clusters on the PCA. So these are just those previous PCA plots, but with the clusters overlaid. So that's the kind of Tenrex cluster, and this was the everything else, the other insectivores cluster, and then golden moles. Okay, so I also ran some of those surface models, trying to look at so surface models measures a slightly different thing. It's looking at convergence in actual evolutionary regimes as opposed to simply convergence in morphology. And the results from that were, I mean, there were results. So I mean, the interesting thing from this is that there's actually convergent regimes within Tenrex. So basically, if the regimes are convergent, then they're the same color. So the important ones I've highlighted are the red ones, because that's the ones that Tenrex involved with. And so there's actually two convergent shifts towards a particular regime within Tenrex separately. But then that same thing also shows up in NOC, which is hedgehogs, which, as we did see in the PCA plots, there was some overlap between Tenrex and these particular hedgehog taxa. So that's, again, sort of everything's sort of converging, pardon the pun, towards sort of at least roughly the same answer. And then from my phenotypic versus phylogenetic distance plots, so the graph on this one here, so this is basically just a plot of phylogenetic distance versus phenotypic distance. And then so each of these points is a pair of taxa. As you can see, there's a lot of points. And so it's probably, the pattern's a lot clearer if I bin them, so that it's not just everything plotted on top of everything else. And so basically, convergent stuff is down here, so where phylogenetic distance is greater than phenotypic distance. So, you know, they are more, for how distantly related they are more similar morphologically than you'd expect them to be. And so yeah, and this line here is just phylogenetic distance equals phenotypic distance. That's just x equals y. Of course, and so I got very excited when I saw this data. I was like, yay, everything, you know, there's all this stuff below the line. There's all this convergence. This is great. Unfortunately, it's not quite so straightforward because you don't actually have a null expectation. So when you make these models, so you don't know what the distribution of stuff should look like, just based on sort of random evolutionary processes. So what I did, so sort of get around that problem, I simulated a load of data on the Brownian motion model, and then I sort of basically subtracted the simulated data from the real data, and sort of basically if you just plot the sort of the residuals, which is on this graph, basically again where there's red, there are more points in the real data you'd expect them to be. Again, quite thankfully for me, there's quite a lot of red underneath the line, so yay, convergence. So there is quite a lot of evidence to suggest that there is convergence going on, unfortunately, but that's sort of between specific taxa. There's not a lot of evidence to suggest that like whole clades are converging on same place in morph space. I'm going to quickly whiz through some. This project is still really its infancy, so there's a lot of future work that needs to be done. The Madagascan tenrecs are an example of not just of convergence, but also of an adaptive radiation, because they're convergent on other things, but they're disparate from each other. So we're going to do some stuff on that, looking at rates of evolution and disparity. I also want to get functional data. I'm a biomechanic by training, so I've got a load of jaw outlines, so I've been turning them into FEA models and then trying to compare those using some new multivariate statistical methods that some friends of mine at Manchester came up with. And also we want to just add more taxa, because the thing about convergence is that it's really scale dependent. If you're just sampling a load of insectivores, then obviously different insectivores will plot out differently. But if you start adding in things like, well, other stuff, things that they're related to, so like the Laurasius-Therian insectivores are related to carnivorans and to ungulates. Obviously, insectivore space is probably different from ungulate space. And so when you start adding in extra things, it's like, oh, suddenly all this stuff clusters into one part of a morph space, and then suddenly it is convergent again. Or is it? We don't know. No one's checked. So again, that's something we're going to try and look at. In conclusion, still a lot of work needs to be done. Thank you to these people, particularly Natalie and Sive, who basically went out and collected all the data before I got involved in this project. And thank you to ProgPal. Thank you to everyone for listening. Any questions?